In section 7.5, we're going to continue to use exponential functions. However, in the last section, we used them for growth models, meaning when things got bigger. But in this section, we're going to use it for decay models, which means that our amount is actually going to decrease. So just as a reminder, exponential functions are in the form of y equals a times b to the x. If it's an exponential growth model, the b value will be greater than 1. And again, that means that whatever we're talking about is getting bigger exponentially, so very big, very fast. If it's an exponential decay model, the b value will be a number between 0 and 1, or just a fraction. So again, an exponential decay model would be as if whatever we're talking about is decreasing at an exponential rate, so it's getting smaller and smaller. In the following examples, we're going to see how to come up with these exponential decay models. So in example number 1 and example number 2, it says write a rule for the function. So just like we did in the last section, your a value is always going to be the number under 0. So we have a would equal 1/2, and your b value is how much you're multiplying by to get to this next number in the y values. So if I take 1/8 times 4, I get 1/2. 1/2 times 4 is 2. 2 times 4 is 8. So your b value is 4. So my final answer would be y equals 1/2 times 4 to the x. Remember, it's exponential if you're multiplying for each successive y value. For example number 2, write a rule for the function. So again, your a value is whatever is underneath the 0. And your b value is whatever you're multiplying by to get to the next number. So notice here, I'm actually getting smaller numbers for the y values. So if I take 5 divided by 5, I get 1. 1 divided by 5 is 1/5. And if I divide by 5 again, I get 1/25. So instead of dividing by 5, that's the same thing as multiplying by 1/5. So my b value is 1/5. So if you notice that you're dividing by 5 each time, that's the same thing as multiplying by 1/5. If I was dividing by 4 each time, I would multiply by 1/4. If I was dividing by 3 each time, it'd be multiplying by 1/3. So always just figure out what the division is and just do 1 over that number for your b value. So your final equation would be y equals 1 times 1/5 to the x. And of course, you don't really need to put this 1 in here. So which one is which? Which one is the growth and which one is the decay? So since our b value is greater than 1 here, this would be a growth model. Since our b value was less than 1, a number between 0 and 1, this would be a decay model since it was getting smaller. And now let's look at an example of graphing an exponential decay problem. So here's example number 3. Graph the function y equals 2 times 1/3 to the x. Identify its domain and its range. So as we said in the previous section, if there isn't a table made for you, you need to make a table for yourself. So I am using numbers from -2 to 2. And then I'm just going to plug those numbers in for x to see what I get out for y. Just like I did before, I'm going to do the work down here and then put my answers in here just so I don't have to squeeze all of my work into these tiny little spaces in the table. So let's start with -2. I'm going to put -2 in for x. It'd be 2 times 1/3 to the -2nd power. So that would be 2 times 1 to the -2nd over 3 to the -2nd. Now remember, negative exponents just make it flip. So I would rewrite that as 2 times 3 squared over 1 squared. So that would be 2, and I'm going to put that over 1 for now, times 9 over 1. So now I'm just going to multiply straight across. Basically, that just gives me 2 times 9 is 18. So at -2, I got 18 for my y value. Now let's move on and do where x equals -1. So I'm going to put -1 in for x, so I'd have 2 times 1/3 to the -1st. So that would be 2 times 1 to the -1st over 3 to the -1st. These negative exponents just make that flip, so that would turn into 2 times 3 to the 1st, or just 3, over 1 to the 1st, or just 1. So I end up with just 2 times 3, which is 6. So at -1, my y value is 6. And now let's figure out what y equals when x equals 0. So I'm going to put 0 in for x, so it'd be 2 times 1 over 3 to the 0 power. Anything to the 0 power is equal to 1, so this is just equivalent to 2 times 1, so my y value when x equals 0 is 2. Next, let's figure out what y equals when x equals 1, so that would be 2 times 1/3 to the first power. So 1/3 to the first power is just 1/3, so that's exactly the same thing as 2 times 1 over 3. So if I multiply straight across, I get 2/3. So when x equals 1, y equals 2 over 3. And finally, let's figure out what y is equal to when x equals 2. So it would be 2 times 1/3 squared. So let's take care of the exponent first. It would be 2 times 1 squared over 3 squared. I don't need to flip it this time because I don't have negative exponents. So that would be equivalent to 2 over 1 times 1 over 9. So I would get 2 over 9 as my fraction. So notice what is happening in our table here compared to what it was doing in the last section. When we had negative x values, we actually got really, really small numbers. Remember, we had those asymptotes where we just got closer and closer to the x-axis, but we never crossed it. So now we're starting off with bigger numbers, and as we get bigger and bigger x value, so as x became positive, then we kept getting smaller and smaller. So this is a reversal of what we were seeing in the previous section, where with negative numbers you should have gotten smaller numbers, like fractions, close to 0, and with positive numbers you got really big numbers. We have the exact opposite of this. So this, again, is going to be a reflection of what we were doing in the last section. So let's get to work with graphing this. Notice that we do not have any negative y values. So just like last section, we do not need to show very much of the negative part of the y-axis. So I'm going to draw my x-axis down here so that I know I don't need to have any kind of negative y-axis at the bottom. But I go all the way up to 18. I'm not going to worry about this 18 because I know it's just going to keep getting bigger and bigger, faster and faster. So I'm just going to start at this 6 and not worry about that 18. And I'll still get a general idea of what the graph will look like. So starting with my graph looking like this, I'm just going to graph these ordered pairs and then connect the points. Remember, this is a nonlinear function, so it should not be a straight line. It should be a nice flowing curve, and we'll see what it looks like. So skipping ahead here, I graphed all the points and look at what I got. So before, with our growth models, it looked like this. We still had a horizontal asymptote along the x-axis because we kept getting closer and closer to the x-axis but never crossed it. And now we have the exact opposite. We start over here big and then we come down as x gets bigger and bigger as we get into positive numbers. So just think about, if I put in a 3, I'm going to get an even smaller fraction. If I put in 4, a smaller fraction. So we still have that horizontal asymptote along the x-axis, but just in the opposite direction. And as I keep getting bigger and bigger negative numbers, I'm going to keep getting bigger and bigger y values. So it's just going to keep getting bigger and bigger this way. So remember, this is just a reflection of our exponential growth. Exponential growth starts here and goes up this way. Exponential decay starts big and gets small. You can actually see it is decaying. It's getting smaller and smaller as I get bigger and bigger x values, which is why it's called decay. And don't forget, it asks you to identify the domain and the range. So just like before, there is absolutely no x value you cannot plug in and take 1/3 to that number and multiply by 2. So the domain would be all real numbers. And the range, kind of like before, I got big numbers this way for y, and as I got closer and closer to the x-axis, but I never crossed over until y equals a negative number. So all of our y values are going to be greater than 0, just like before, because we don't get any negative y values, and it just keeps getting bigger and bigger and bigger. But it's never equal to 0, so that's why it's just strictly greater than 0. Next, we have a concept summary, the exponential growth and decay, just like I was talking about before. For exponential growth, your a value is going to be greater than 0 and your b value is greater than 1, and it will look like this, where you start off really small and you keep getting bigger and bigger. If your a value was less than 0, it would just be down this way, but it still is going to get bigger and bigger as I go this way. For exponential decay, if your a value is greater than 0, and your b value is between 0 and 1, it's going to start off big and get really, really small. If your a value was less than 0 or a negative number, it would look like this, but still keep getting smaller and smaller as you get bigger and bigger x values. So I would just jot this down in your notes so that you know what is a growth and what is decay and what it looks like as far as graphs. Next, we have the exponential decay model. So just like we had the exponential growth model, it'll look a lot the same. The exponential growth model had a plus sign here rather than a minus sign. So that's the difference between exponential growth and exponential decay. You still have your initial amount, A. You still have your decay factor. This was before called the growth factor. You're going to take 1 minus your decay rate instead of 1 plus your growth rate. R is the decay rate, and remember that's always going to be as a decimal. And the t value is the time period, and typically that's going to be in years. So again, this is just like when we did exponential growth. The only thing that is different is that now we are subtracting the decay rate because things are getting smaller, so it makes sense to subtract it. If things were getting bigger, it makes sense to add it. So it's exactly the same thing. We're just subtracting the rate rather than adding the rate. So let's see an example of a decay model. Example number 4. A farmer bought a tractor in 1999 for $30,000. The value of the tractor has been decreasing at a rate of 18% per year. So part A says write a function that models the value of the tractor over time. So since it's decreasing, we know we're going to use our decay model, not the growth model. So we're going to start with y equals a times 1 minus r to the t power. So we need to identify first our a value. So our a value is the initial amount, which is $30,000. Then we need the R value. It said 18% per year. So as a decimal, that would be 0.18. So our model would be y equals 30,000 times 1 minus 0.18 to the t power, because remember this is our variable. So the only thing that I would do is just simplify this. So I would end up with y equals 30,000 times 0.82 to the t power, and that would be my exponential decay equation. So for part B, it says, what was the approximate value of the tractor in 2005? So it was bought in 1999, so in 2005, that is 6 years later. So I'm going to put 6 in for t, so it'd be y equals 30,000 times 0.82 to the 6th power. So I'm just going to type that into my calculator, round to 2 decimal places since it's money. So I get about $9,120.20. So that's how much the tractor would be worth after 6 years. That's not very much if you spent $30,000 to start with. So that's it for this section. Make sure you jot down anything you didn't understand that we can cover in class before we move on, and we'll see you then.